Hello students, this is Professor Chalai, and in this video we're going to look at covalent bonding, electronegativity, and bond polarity. As always, you can follow along with Chapter 7 workbook. By the end of this video, you should be able to describe the formation of covalent bonds, you should be able to define electronegativity, and you should also be able to assess the polarity of various bonds. Let's get started. So earlier we talked about how a covalent bond is just this idea where the atoms share electrons, right? It's usually bonding between two non-metals. So let's write that as a definition. In a covalent bond is simply the sharing of a pair of electrons. And usually this happens between nonmetals, but we'll get to that in a bit. Now, this idea of a pair of electrons is also something that we're going to get to. Why is it a bond? Why is a bond specifically a pair of electrons? That's something we're also going to get to in a later chapter, the next chapter actually. Okay, let's see why this happens. This sharing of electrons happen from an electron configuration point of view. So by now we recognize that oxygen just doesn't exist as a single atom. We went over in the last video why this might not be, because it's not really stable. From the electron configuration is not very stable. We know that oxygen exists as O2, right? And we know that oxygen, being a nonmetal, when it forms a bond with itself, it will form, two nonmetals together. It will form a covalent bond. But let's look at it from the idea of sharing. Okay, so let's look at a periodic table. And let's look at oxygen. It's right here. So electron configuration will start with helium, and then we'll have the 2s, and the 2p will have 1, 2, 3, 4 electrons in it. So if we're looking at oxygen, right, on oxygen, it'll have a 2s and a 2p orbital. The 2s will have 1, 2 electrons in it, and the 2p will have 1, 2, 3, 4 electrons in it. Okay, so now we're looking at two different oxygen atoms together, right? Because we're looking at O2 molecule. And I just want to show you why this happens. 2p, and I will use, I don't know, blue color for the electrons here. 1, 2, 3, 4, 5, 6. That's the electron configuration of two oxygen molecules. Remember I mentioned that we don't want to have a randomly filled shell, a randomly filled set of orbitals with the 2p orbitals here. In fact, this electron atom on top wants two more electrons to fill its shell, and the one on the bottom similarly wants two more electrons to fill its subshell. So what if the one on top borrows those two electrons from the bottom here sometimes, so that it could pretend that it has a fill subshell? And what if the one in the bottom sometimes borrow those two last electrons to fill its orbital, so it can pretend like it has a fill orbital as well? That's what we mean from an electron configuration point of view when elements share the electrons to form a covalent bonds. Sometimes the one on top will borrow these two electrons from the bottom so it can have a filled subshell, and then sometimes the one on bottom will borrow the electrons on top so that it can have a filled subshell. So if you think about it, these four electrons are the same electrons, right? Just sometimes they're on this atom, and then sometimes they're on this atom. So if I were to draw that, here's one atom, here is the second atom, and we have these four electrons. Sometimes they're on this atom, and then sometimes they're on that atom. And they just sort of share electrons that way, and they form a bond. And there are two pairs of electrons here, so really they form a double bond, but we'll talk about that later when I draw a triple bond there. I don't know why. It's a double bond. We'll talk about that later, why it's a double bond. But this is electronic configuration point of view of why nonmetals might share electrons. They really do that to, be happy. And they're only really happy when they completely fill their orbitals or completely empty their orbitals. Now, you might think, okay, fine. Two atoms are sharing some electrons. that sounds good enough. But we learned from our previous chapter that atoms or elements don't pull on electrons the same way. For example, we learned that the more towards the right side of the periodic table you go to, towards the nonmetals, they tend to pull on electrons more than elements towards the left side of the periodic table, right? So you might imagine they might share electrons unequally. Well, sure, that's true, but how do we determine how unequal or equal two elements might want to share some electrons? Well, to understand that, we need to look at this idea of electronegativity. And as you might expect, electronegativity is simply the tendency of elements to pull electrons to themselves. So let's write that first. Electronegativity is the tendency of an element to pull electrons to itself. And as you might suspect, the more towards the right side of the periodic table you go to, the higher the electronegativity value is, because the more likely those elements are to pull electrons to itself. Similarly, as you go down, or rather oppositely, if you go down the periodic table, there's a decreasing electronegativity because those elements tend to not pull electrons to themselves. So as you might expect, fluorine here has the highest electronegativity value in the periodic table, and as we go sort of to the left and down, francium has the lowest electronegativity value. So what that means is, what's important is the difference in electronegativity value. If you have two elements of fluorine bonded to each other, right, they're going to be pulling on the electrons equally. Even though they pull very strongly on the electrons, they're going to pull on it very equally, and so there's no unequal sharing of electrons there. You have two identical elements. But if you have, let's say, fluorine and, I don't know, something like nitrogen bonded to each other, right, nitrogen and fluorine, well, fluorine has a much higher electronegativity value than nitrogen, so you might expect that the fluorine will pull on the electrons more strongly than the nitrogen, and so there'll be an unequal sharing of electrons. So, like in most cases, things are never going to be as simple as just covalent bonds or ionic bonds. So we'll separate things into what we'll call pure covalent bonds and polar covalent bonds, and then on the extreme side, we have ionic bonds. And we're going to define things as pure covalent or polar covalent depending on how different their electronegativity values are, right? So in the case of, let's say, fluorine and, well, let's not pick fluorine because fluorine is so strong. Let's pick, which two? I don't know, chlorine and bromine, right? Chlorine and bromine, they have different electronegativity values, but they're not very different, right? The difference here between 3.0 and 2.8 is just 0.2, right? They pull on the electrons differently, but not so differently. So they end up sharing it pretty equally when they pull on the electrons. So that means that they have a pure covalent bond between them, because their electronegativity difference is sort of between that 0 to 0.4 range. However, if we were talking about, let's say, fluorine and chlorine, so let's look at fluorine and chlorine now, right? So fluorine, chlorine, their difference here is much bigger, right? There's a difference in electronegativity value of about 1.0. Fluorine is much stronger than chlorine, so fluorine will end up pulling on electrons a lot stronger, and so what we'll end up having is what we call a polar covalent bond. And these are important. So for polar covalent bond, their electronegativity difference lie between about 0.4 to about 1.8 region. And if their electronegativity value is much larger, the difference is much larger than that, then we have what we talked about earlier, which is an ionic bond. So you can think of bonding as lying on a spectrum between pure covalent all the way to ionic, right? So in a pure covalent bond, like we showed with fluorine and fluorine, they pull on the electrons equally, so there's no charges anywhere. For an ionic bond like lithium fluoride, right, their electronegativity values are so different, we know that in fact lithium forms a positive 1 charge and fluorine forms a negative 1 charge. So we'll write positive and negative there to show the charges between them. So this is a pure covalent bond because they share on it equally. This is an ionic bond because we know that they form ions. In between, we have this polar covalent setup with, what's the example that we used? We used fluorine and chlorine as an example. Polar covalent, if I can spell correctly, covalent bond. And we know that fluorine pulls on electrons just a tiny bit more than chlorine, so this will end up forming a tiny positive charge, and this will form a tiny negative charge. This symbol here, this is delta. It's the Greek delta. It's a lowercase delta. We know that we looked at this as uppercase delta, and this little symbol here is a lowercase delta. It kind of looks like a D with a little squiggly there, so like that. So lowercase just means, lowercase delta here just means a small amount. Small amount. So a small amount of positive charge and a small amount of negative charge, and that's what we have in a polar covalent bond. Right, so in these bonds, since there's a slight positive charge, I did that opposite, didn't I? There should be a slight negative charge. There we go. Slight negative charge here because it pulls on electrons a little bit more, and so chlorine will have a slight positive charge. You have an extra negative charge here because there's a little bit extra electrons on the fluorine. All right. So in this case, because there's a slight pull of electrons towards the fluorine, we'll have what we call a dipole moment. And we will draw dipole moments by drawing little arrows with a little line through the arrow on the tail of the arrow. And the arrow will always point towards where we have the negative charge. So there we have it. We have polar covalent bonds, and we have the dipole moment to show the direction of the electron pull. And so we have the definition of a dipole moment here. We usually use this symbol. This is a Greek symbol mu, right? It looks kind of like a U with a little extra curve in the beginning. So the Greek symbol mu for dipole moment, it occurs anytime there's a separation of positive and negative charge, typically. And dipole moments in bonds are represented by arrows like I just showed you, where we just point the arrow towards the side with the negative charge. Okay, so with that, let's look at all of these different compounds. Let's try to figure out whether they'll be pure covalent or polar covalent or maybe ionic, depending on what the differences in their electronegativities are, and if they are polar covalent or ionic, we'll draw dipole moments. All right, so chlorine, Cl2, we know that these elements are the same, so they're going to pull on this bond equally in equal opposite directions. So there's going to be no charges anywhere, even partial charges, and so this is going to be what we'll call pure covalent, and there's going to be no dipole moments. Let's look at ClF. This is one that we already looked at. Cl bonded to F. F pulls on electron tiny bit more. That's because F has a electronegativity value of 4.0. Chlorine has one of 3.0. So the difference here is 1.0, which falls into the polar covalent range. So this will be polar covalent. And because it's polar covalent, we will draw the dipole arrow, which I have already drawn, but I'll use a different color, the dipole arrow. And because F pulls on the electrons just a tiny bit more, it'll be a negative charge. Again, I want to use a different color, orange, why not? Tiny negative charge, which means the chlorine will have a tiny positive charge. All right, let's look at HF. H bonded to F. We already know that fluorine has an electronegativity of 4.0. What's the electronegativity of hydrogen? Let's look at it. It's 2.1. So 2.1, which means the difference here is 4.0 minus 2.1. That gives us a difference of 1.9, if my math is correct. So 1.9, if we'll see here, 1.9 actually falls in the ionic category. So in the ionic category, the pull of fluorine is so much stronger than hydrogen that it doesn't form a partial negative charge, it forms a full negative charge, which means that hydrogen is missing one of its electrons, so it's a full positive charge. The dipole moment is still in this direction, but because fluorine completely pulled the electron away from hydrogen, right, because of how strong it is, it falls in the ionic category, they actually form ions, and so this would be ionic bonding. So you can look at this table of electronegativities and then look at this chart for electronegativity differences, and you can figure out which compounds form covalent bonds, which pure covalent bonds, which ones form polar covalent bonds, and which one form ionic bonding, ignoring whether they're metals or non-metals or any of that. Again, let's look at lithium fluoride. I think I mentioned lithium fluoride earlier. Fluorine has a very high electronegativity of 4.0. Lithium has a very low electronegativity of 1.0. So the difference here is 3.0, which is very ionic, if such a thing exists. So this means that fluorine will completely pull the electron away from lithium, forming a negative charge. Lithium has a positive charge. Our dipole moment will then point in that direction. And then again, this is ionic bonding. You can do this for any pair of element in the periodic table. For example, maybe you want to try carbon-hydrogen bonding on your own, or carbon-oxygen bonding, or carbon-nitrogen bonding. Those are bonds that pop up often. There's even oxygen-hydrogen bonds and nitrogen-hydrogen bonds that also pop up often. Try to figure out whether these are pure covalent or polar covalent, and try to draw the directional arrow for the dipole moment. All right, so this will bring us to the end of this section. Just to reiterate, we went over the idea of electronegativity, which helps us to classify different bonds as either pure covalent, polar covalent, or even ionic, based on how different their electronegativity values are, right? And just to reiterate, if they're pure covalent, it means that their electrons are shared equally, so there's no partial positive or negative charge. If they're shared unequally, there's going to be a partial positive charge and a partial negative charge. And if they're shared completely, if it's completely transferred, then there's going to be a complete positive charge and a complete negative charge. Here, there's 0 charges. All right, that'll bring us to the end of this section. In our next section, we're going to look at Lewis symbols and structures. I will see you then. Bye.